how do you teach a machine to think? I mean, really think. It's one of the biggest questions in AI, and today we're going to peek behind the curtain. We're going to put together a toolkit of all the best practices that take a basic, clumsy neural network and turn it into a powerful, stable learner. Let's get right into it.
So, you might be asking, why is this so hard in the first place? Well, the thing is, training an AI model is notoriously tricky. It's not some simple, straightforward process. Nope, it's this incredibly delicate balancing act. If you get it wrong, you end up with a model that has learned absolutely nothing, a complete dud.
You see, when you start out, a brand new neural network is basically what we'd call an unstable learner. Just imagine for a second that you're trying to find the lowest point in a huge, hilly park, but you're blindfolded. You'd probably jump around randomly, get stuck in little dips thinking you find the bottom, or just wander for hours, right? Well, that's our starting point with AI.
Okay, so the very first problem we've got to solve is speed. How fast should our model actually update what it's learned? Is it better to be super caffeinated, like an espresso shot, reacting to every single little thing? Or should it be more calm and deliberate, like a chamomile tea?
It's fascinating when you look at the two extremes. On one hand, you've got the espresso shot, that's stochastic gradient descent. It updates the network after every single example. It's fantastic for jumping out of bad solutions, but it's so jittery and chaotic, it often jumps right past the best solutions. Then on the other side, you have the slow brewed chamomile tea, batch gradient descent. This one waits to see all the data before it makes a single update. It's stable for sure, but man is it slow, and it can get stuck really easily.
So here's the key takeaway. Neither of those extremes is really what we want. The solution, the thing that actually works, is a beautiful middle ground, mini-batch gradient descent. Instead of looking at just one example, or all of them, the network processes a small, manageable batch, like 32 or 64 examples, and then it updates itself. And this is the perfect balance. Mini-batching is our green tea. It gives the model a steady stream of updates, just enough energy to keep it from getting stuck, but without all those chaotic jitters from the espresso shot. It is by far the practical, effective standard for almost all modern AI training.
All right, we've set the right pace. That's a huge step. But the landscape of the problem is still, well, it's treacherous. It's full of hills and valleys, and our little learner can still get stuck. So how do we help it navigate this complex terrain?
The first tool we pull out of our toolkit is momentum. And the idea is actually pretty simple. Instead of just looking at the slope of the hill right where we're standing, we also take into account the direction we were just heading. It's like giving our learner a little memory of where it came from, helping it build up speed as it moves in a consistent direction.
To really get this, picture a sled way up on a snowy hill. That sled is our learner. As it starts sliding, it builds up speed, it builds up momentum. Now, what happens when it hits a small ravine, a sort of suboptimal solution where it might get stuck? Well, that built-up speed carries it right through the bottom and up the other side, so it can continue down the hill towards a much deeper, much better valley. Without momentum, it would have just stopped dead in that little ravine.
But okay, this brings up another little wrinkle. Using just one single speed, or learning rate, for the entire network, well, it's not ideal. Some parts of the network might need big, fast adjustments, while other parts need much finer, more delicate tuning.
And the solution is one of those brilliantly simple ideas: adaptive learning rates. This technique gives every single parameter in the whole network its own personal learning rate. And what's even cooler is that this rate actually changes and adapts all on its own during training based on how much that specific part has been updated in the task.
Now here's the good news. You don't have to code all of this stuff from scratch. Modern deep learning libraries package these concepts, momentum and adaptive learning rates, into these incredibly powerful optimizers. You've probably heard of names like Atom or RMS Prop. Well, these are the engines that are really driving efficient AI training today.
Okay, so far, we've been focused on the training process itself. Now let's pop the hood and look at the network's internal components. Because just like with a car, the parts you build it with matter just as much as how you drive it.
Let's start with something called activation functions. You can think of these as the on-off switches for each neuron. The old school ones, like Logistic and TAN, had this huge flaw. At the extremes, the signal they sent about which way to learn got so tiny it would just vanish, basically stopping learning in its tracks. The modern choice is ReLU. It's way simpler, way faster, and it doesn't have this problem, for positive values at least. Its only little quirk is something called the dying ReLU problem, where a neuron can sometimes get stuck permanently in the off state.
All right, next question. How does the network even know if its guess is good or bad?
That is the job of the cost function. It's basically a math formula that measures the distance between the network's prediction and the actual right answer. High cost means a terrible guess. A low cost means it's getting close.
Now, while mean squared error is pretty simple, it can cause the same slow learning problems as those older activation functions. Today, the absolute gold standard is cross-entropy. It's mathematically designed to work perfectly with modern networks, and it completely avoids those learning slowdowns. It's the go-to choice for pretty much any classification task you can think of.
So we've built a stable, efficient learner. But there's one final, absolutely critical hurdle. We have to make sure our network is actually learning the general rules and not just memorizing the answers to the test.
This problem has a name, overfitting, and it is the enemy of true intelligence. An overfit model is like a student who memorized every single question from last year's exams but can't solve a brand new problem because they never actually understood the concepts. That kind of model is completely useless in the real world.
So how do we force this thing to do some disciplined studying? Well, there are two main tricks. First is regularization, which adds a penalty to the cost function. You can think of it as a tax on complexity that stops the network from relying too much on any one connection. And then there's dropout, which is a really clever, kind of wild idea, where we just randomly turn off parts of the network while it's training. This forces the neurons that are still on to become more robust and less dependent on each other. And we're not talking about a trivial amount here. A typical dropout rate is around 30%. That means while it's learning, the network is constantly being forced to work around a third of its brain being randomly unavailable. It's a powerful way to build a learner that's truly robust.
So there you have it. That's our toolkit. We've got mini batching for the right pace, momentum to navigate the landscape, better internal parts, and tricks like dropout to make sure it's actually learning. This is what makes modern deep learning even possible. So the question that leaves us with is this. Now that we know how to build stable learners, what's the next great challenge we need to solve to build even better ones? Something to think about.